scientists. Ladies and gentlemen, emerging technologies are the technical innovation that provide huge advantage in many aspects. Emerging technologies can improve people's life in many ways. Technological advancement can help people complex tasks more efficiently, keep them safer and healthier, and protect environment. These technologies are still underutilized and underutilized. The purpose here is to recognize the technological advancement in the field of science and technology and their huge dramatic effect and apply them for the socio-economical well-being of residents of OIC member states. Today, we are very fortunate that we have a very eminent scientist with us, Professor Dr. Abdolreza Simchi. He is a distinguished professor in engineering science and material engineering, Sharif University of Technology. And it's my great honor, to introduce all of you with Professor Raza Simchi. He is distinguished professor and a fellow of Alexander von Humboldt Foundation, Germany. He is among the top 1% highly cited material science scientists in Web of Science and ranked among the top 150 scientists worldwide in emerging and strategic technologies. Materials identified by Stanford University 2021. He has received many national and international awards, including George Foster Research Award, Khwarizmi International Award, World Intellectual Property Award as Best Young Inventor, UNO, EPMA Award for Material Development, Dr. Dr. Mojtahidi Award for Technological Development, Royal Society Fellowship, Nano Award, and many more. He's recognized by the National Nanotechnology Initiative Council and National Elite Foundation as one of the most influential scientists of this field of expertise. The activity of Dr. Simchi spanned a broad area of synthesis and characterization of nanostructure for biomedical energy and sensing applications. He has been author and co-author of 4 books, 3 book chapters, 10 patents, and over 300 peer-reviewed papers, which have been cited over 40,000 with an H index of 62. He is also the editor or member of editorial board of many ISI-ranked journals and frequently serves as the referee of high-effect factor scientific journals. With this introduction, I request Dr. Abdolreza Simchi for his talk. Over to you, sir.
Thank you very much, Chairperson. My voice is clear, right?
Yeah.
Okay. Ladies and gentlemen, I am very pleased to give you a lecture at Comstech lecture series. As chairperson kindly introduced me, my name is Abdolreza Simchi, also known as Arash Simchi. What I would like to talk today is about the application of nanomaterials in medicine or nanomaterials in biological applications. As you know, there is a wide, vast area of application of nanomaterials in this section that I would like to pick some highlighted topics and which is important nowadays. For the start, I would like to introduce Sharif University of Technology very briefly. Sharif was founded in 1966, about 54 years ago, and has about 475 faculty members, 10,000 students, about 50% are graduate students, and 37% are female, which is really good considering a technical university. For a long time, Sharif University of Technology has been recognized as the top engineering science department and institute in Iran and also in the Middle East. I personally work at the Department of Material Science Engineering and run as a director of Nanostructure and Advanced Materials Center. This center was founded about 20 years ago, And the main focus of activity is in 3 different areas. One is nanobiomaterials, development of functional materials for biomedical applications, which is the topic of my talk today. The other section is electroactive materials, as you know, for energy conversion, for energy storage, and so on. And the third section is renewable energy, solar cells, and so on. As I mentioned, I'm going to give a lecture today on the first topic, which is the nanobiomaterials. And you see my group is a little bit large, about 20 graduate students and postdocs are working here. If you would like to have a perspective about nanomaterials, as audience know that usually we divided nanomaterials to 0 dimension, 1 dimension, 2 dimension, or 3 dimension. From the 0 dimension, which we're particularly interested in nanoparticles, what we use for biomedical application could be organic, inorganic, or hybrid organic, nanoorganic. It's very important to be smart. So it means that it might be temperature sensitive, pH sensitive, or so on, which we use it for drug delivery or other applications. And it's absolutely important to be functionalized for special properties that is needed for biomedical applications. Concerning one-dimensional nanomaterials, we usually refer to nanorods. Nanorods has a special property. I will show that the bioactivity of nanorods could be better than one-dimensional materials or macroparticles. One special advantages of nanorods are transport properties, for example, electrical conductivity, which is important for some application, especially biosensing. And I will show that nanorods could show antimicrobial effect that is important for many applications in medicine. The other topics are.
Professor Simchi, your screen is not visible. Have you shared it already?
Yes, I shared it, of course.
No, we cannot see your screen.
Is it shared? Is it shared? Let me do once more. Why not? Is it not shared?
Yeah, now we can see it.
Have you seen it? When I change the pages, you see it?
No, not before, but now we can see your first slide.
Okay, just the first slide, not the second and third one?
Yeah, we can see your first slide now. You can go in slide share mode.
Yes, it is in a slide share mode, but you see it now, right?
Yeah, we can see, yeah.
Okay, I'm just on the last slide 4. I'm sorry, I don't know, I was sharing it. The third section is ultra-thin layers, 2-dimensional materials, which for some reasons we use it for biomedical application. For example, we use 2-dimensional material like a graphene, laponite, or so on for mechanical effects to increase the mechanical properties of polymers, or change the gelation time or flowability of hydrogels, or we use them as a carrier for biomacromolecules.
I'm sorry, Professor Simchi, to interrupt you, but we cannot see your slides moving. We are only stuck on slide number 1, and this is not in the full screen mode also.
It is very strange because I am in the full mode, and also I share it. My say it's shared.
Yeah, we can see the slides, but they are not in slideshow mode. The full screen.
but it is in full screen. You don't see, I am now in the slide 4, and it's the full screen share.
Okay, now you can continue. It's fine, but this is in the slide panel mode, not in the slideshow mode. But this is fine. You can continue.
It's strange. Do you want me to? That could be. Could that be from the low internet speed? Should I turn off my camera to have a better speed? Do you recommend that?
I think it's okay. You can continue.
Yeah. Well, I hope, but my computer is in the full screen mode. Anyway, I continue it. Sorry if it's a problem of the virtual meeting. Anyway, in a bulk nanomaterials, we also work on some kind of making scaffolds, which should be printable or injectable, and many of them are fibrous, so the cells can stick to the surface and better proliferation. It is also possible to load cells inside the scaffolds. The scaffolds can be functionalized. And the most important link, by the development of additive manufacturing and bioprinting, the scaffolds can be personalized. So we can go to the personalized medicine. With perspective of the applications, if you see number 5, the slide number 5, I just made a categorize of that. Perhaps one of the most important area are regenerative medicine, which we use biomaterials or nanobiomaterials to regenerate a tissue. The other topic is drug delivery and therapy that can be used for cancer therapy or tumor therapy or so on by nanocarriers. The next slide is bioimaging, which we use the nanomaterials to image a tumor inside the body, or when we treat a cancer, we monitor how the process goes on. And the next section is biosensing, as you know.
Sorry to interrupt you again, but I don't know what is the problem, but slides are not moving. We are stuck on, yeah, we are stuck on slide number 4, which is nanomaterial perspective. I'm really sorry, but I don't know what is the problem. Why don't you just close it and then share it again?
Yeah, I do. Let me to do it again. I am sorry, I don't know what's the problem. I really don't know what's the problem. But for my computer, it's shared. And Zoom. Is that visible now?
Yeah, we are on slide number 1.
Still number 1?
Yeah, number 1, and it is not in full screen mode.
It's very strange. Let me to leave the room and come back again, okay?
Okay, sir. Okay. दोबारा आएंगे तो वो slide दीजिए.
I am just coming back. I just try to share once more.
Okay, sir.
I don't know what's this problem is. It's terrible. Why it is so? Okay, I come back again. So I just put in the slide mode. Do you see full screen?
I'm really sorry, but sir, no, we are again on the screen number one. When you are clicking this full screen mode, it's not, yeah, it's not in full screen mode yet.
It's not in full screen yet. It's strange. It's really strange. Because in my computer it shows that the screen is shared. The screen is shared, and it's in a full mode.
Okay, so I think what we can do to save time is you just read the slide number, and then whenever you change the slide, you just say it that slide number 5 or whatever, and keep on
Yes, I
changing.
do.
Yeah.
But now I am in a slide 5. Is it okay?
We are on slide 4.
Still 4?
Yeah, now we are on 5.
It seems that whenever I make it in a screen mode, it's a stop. It seems so. It's like this. So I keep it in this way. I think maybe it's better. Not a full screen, but just a normal screen. Is it okay?
Yes, this is fine.
Okay, it's pity because I lose some function, but at least I can speaking. I am really sorry. I don't know what's the problem, but in my computer it's in a full screen mode. Anyway,
No,
as I mentioned, the field of application of nanomaterials can be in regenerative medicine, in drug delivery, in bioimaging, in biosensing, in biological MEMS, and bioinformatics. I would like, in this section, I would like to talk a little bit about the first 4-1. So I start with regenerative medicine as the first topic. I turn to slide number 6 now. As you know, tissue engineering, we use biomaterials to play an essential role in generation of implants by controlling the cellular microenvironment. There are a lot of work in this topic, and for bone tissue engineering, for cartilage tissue engineering, for skin or nerve, and also very recently for health. I would like to show you some examples of successful application of tissue engineering scaffolds. At the start, we maybe some years ago, we start on hard tissue implants. As everybody knows, there are in market a lot of titanium implants that can be used for hard tissue engineering. For example, titanium alloys are very famous. However, what is going on is the titanium surface is not bioactive. On the other hand, after implantation of a hard tissue like titanium, and the patient needs to be hospitalized, and there is a lot of efforts for taking antibiotics because to combat the bacterial effects. We had in mind with Professor Bucacini in Imperial College to create a thin layer on the surface of titanium by a polymer material which has contained bioactive materials, antimicrobial agents, and also nanomaterials. Therefore, what we did is to use electrophoretic deposition, as you see in the SEM pictures and images. we use, for example, chitazone embedded bioactive glass particles inside and try to incorporate vancomycin or other biomolecules inside the polymer matrix and to control the release of drug. However, the problem is we could not control the drug release rate. To do so, we incorporated also reduced graphene oxide inside the polymeric matrix and conjugate the drug to the nanomaterials by functional surface functional groups. The result was very interesting, as you see here in this figure, in the right downside, if it is visible. The low image shows the release of drug. As you see, after 12 days, it's almost finished. But the upper the curve shows the incorporation of vancomycin conjugated to the graphene oxide. We could load in more drugs and release it for a longer time, which is very helpful for practical application. I turn to the slide 8, if it's visible. We tested antibacterial effect of such a coating on titanium. As you see in the left-hand figure, the antibacterial effect depends on the concentration of the drug loaded inside the coating. And also we did a different examination from the cytotoxicity of the system, because there's always a risk of the nanomaterials inside the coating for biomedical application, and we could not find really an intensive effect on cytotoxicity. On the other hand, we have found that the ALP activity is high and the cells stick to the surface, so there should not be a problem. In the next run, we tried to develop antibacterial surfaces by combining nanorods and graphene oxide layers to make it light active. So when the light stick to the hit the surface, the surface, especially the functional groups of graphene oxide, creates functional groups that can stick to the bacteria and kill them. To do so, we used I am on the slide 10 now. We developed a procedure to grow well-aligned nanorod of copper oxide. As you know, copper oxide is also light active, and then confocally coated it by graphene oxide layers, as you see in figure D. And then we examined the antibacterial activity under light and without light. And you see here in the middle figure that the materials containing nanorods with a confocal coating of graphene oxide shows extremely active antibacterial effect. The red line in the graph in the right side. So this is another step forward to incorporate nanomaterials, combine it with a semiconductor, and make it light active for antibacterial surface effect. Then we thought, okay, with the emergence of additive manufacturing, we thought it's very interesting to make bone scaffolds or bone insert via additive manufacturing. At that time, bioprinting was not very popular, so we used inkjet printing to make sacrified molds. As you see here, the sacrified molds from the plaster is made by a special porosity which is needed for a scaffold, and then fill it by composite materials that could be a polymer incorporated with nanoparticles, bioglass, heteroxyapatite, and so on. Did freeze drying, and then remove the mold to make a three-dimensional scaffolds. And this gives us an opportunity to design the porous structure of the system. Especially, we have found, I'm going to slide 11 now, especially it is very important to have the material with a porosity gradient. So, for example, if you want to join a bone to a cartilage, it's important to have a porosity gradient so different cells can interpret and ingrow inside the porous structure, as you see in the SCM structure of our scaffolds. And then we have found that the tissue are well grooved in the system inside the pores and makes the pores very circular, as you see here, the confocal image in the middle of the slide, the confocal image of the stained osteoblast cells that stick to the surface, develop a tissue. And interestingly, we did an ALP analysis and showed that the 3D pore structure even works better than a flat surface. So when there is a curvature in the pore structure, the cells stick better to the system and grow inside the pores to prepare to generate a tissue, for example, a bone tissue in the system. However, we use nanoparticles of the bioglass, and we found that the bioglass is not very stable inside the body, and sometimes we will have some kind of cytotoxicity. Therefore, we thought it's better to use hydroxyapatite, but as you know, hydroxyapatite is may not be as active as nanoparticles. There are some commercial available particles, but we found that it's very interesting if we could develop hydroxyapatite from natural sources. For example, we can use it from the bone or teeth. We have especially developed a procedure to transfer teeth to hydroxyapatite nanoparticles and nanorods. And it's subjected to a US patent in 2019. And in the left-hand side, you see the Alziran red qualification assay. The top figure, number A, is a control. B is nanoparticles, C is nanorods, and D is micrometric particles. As you see, number C, the nanorods are very active. Therefore, we have shown that when we drive nanomaterials from biowaste, from the body, from the teeth, or from the bone, it works even better when we synthesize from the chemical materials. In following, we use these materials to make polymeric scaffolds for as bone inserts. And the question was, we cannot use bones always, the human bones on teens. We have to find another biowaste. Therefore, we use oyster shells, which is available quite easily from the south of Iran and many Islamic countries. We use our developed procedure and made scaffolds from gelatin and metal cellulose. And then we have shown that the scaffold works very well in the body and develop the mineralization, and therefore can be used for bone regeneration. In following, we decided, the slide is clear, right? Just note me that the slides are clear. Is the slide clear, sir? Hello? Please remind me, is the slide clear?
If this is visible to us, sir, it's clear.
You see it, okay. Okay, I try to make it a slideshow and then come back to everybody with this, you see. With the emergence of bioprinting, we decided to develop our procedure that prepare scaffolds that is printable. One of my PhD students used electrocatalytic polymers and electroactive polymers. The polymers and the polymers that have a minus and plus surface charges, combine them together, add laponite to them to make the GAG nanoparticles as is shown in the figure. And she was clever to show that adding the lapunite nanoparticles, which are the two-dimensional ceramic nanoparticles, to transfer the GAG nanoparticles to a gel. And this brings a significant opportunity to manufacture scaffolds, which is printable. And the most important things from this work, which is published in Biomaterials, we show that the gelation is reversible. So when we prepare the material as a gel, it's a solid material. When we insert a force on that, insert a shear on that, it turns to a liquid. And this process, as you see in the right-hand side, this process is reversible. So this can change from the gel to liquid, gel to liquid. So we prepare the material, we print it very easily by inserting force. And as far as it is printed, then it becomes a gel and make it stiff. That creates a, and the problem, and the most important thing is that these materials are printable, and also we are able to load cell inside the printing. As you see here in the left-hand side, the GAC nanoparticles is combined with are combined with lapunite, and we also loaded W2070 cells inside and then printed as a scaffold, as you see in this figure. And then we use these materials. We did a lot of cell response and cell studies and in vivo studies. The result was very interesting. First of all, we have shown that the cells sticks to the surface and alive in the matrix of the printed scaffolds. As you know, bioprinting has a challenge to load cells inside and could have live cells after bioprinting. So the cells are alive. And then by using ALP activity, as you saw in the right-hand side figure down, that the AL activity is high, therefore the cells are active, they can proliferate it and do bone regeneration. In following, we had in mind to create and to fabricate injectable self-healing adhesive hydrogels. So we go a one step forward to make our hydrogel not only printable, but also light active. And it means that by irradiation of light creates antibacterial effects. And also the gels could be self-healing. So we use natural biopolymers containing upconversion nanoparticles, and we show that the gels can be cut in two pieces, as you see here in the left-hand side, cut a scaffold in two pieces and put it together, and again, they integrate and make a three-dimensional scaffolds without any problems. So the gel has a self-healing properties and has very adhesive properties. And then we use light. So we irradiated light to the system, 800 nanometer with a wavelength of 800 nanometers. And we show that the temperature, and we measure the surface temperature of the gel. And you see the temperature of the surface dependent on how much nanoparticles are added to the system. The temperature increased and killed bacteria. This is a unpublished work, very recent work of our groups, as a development of the previous work. The next step was one of our colleagues tell me whether we can make it printable. So we don't want to just cast the gel, but also we would like to use it for 3D bioprinting. So we try to do it as you hear. We use silver nanoparticles in the shape of triangular. And the importance of this action that we would like to have a wavelength of about 800. As you know, the red light is very good for deep penetration, so we can use thermal treatment in a deep tissues. And then we printed the gels. We could successfully print the gels, as you see in the figure, top right figure, and then examine the temperature increase with time of irradiation. As you see, the temperature can reach to the 40 degrees centigrade, so the cells can be killed. It's not only the bacteria we have in mind. As you know, there are a lot of effort for cancer therapy. So we are trying to develop a hydrogel system, injectable system that inject in the body, in the site of cancer, and then we irradiate light to the system, and the temperature increases to kill the cancer cells. This is the aim of this effect. The next step, we try to do some work on the cartilage engineering. As you know, cartilage in tissue engineering is very difficult because the chondrocyte cells are difficult to regenerate. I had students that had in mind, said to me, I can make a special polymer and hydrogel specifically for cartilage. And he used a polyethylene glycol and terminated the end functions by amine groups. And then add laponite, two-dimensional inorganic material inside, and then load the cells, stem cells inside, in order to regenerate the cartilage. It is really ambiguous research because first of all, the mechanical properties is important. Second of all, it should be injectable because we don't want to have invasive surgery for cartilage repair, and it also have to make a platform for regeneration by stem cell therapy. He was successful to prepare such polymeric materials, and I will show you some results about that. The SEM picture in the left-hand side show the structure of the hydrogel he made. The middle picture shows the gelation time and the viscosity versus the shear rate show it is an injectable and it can be a gel after 10 minutes. And cell studies shows that the stem cells remain active and can be proliferated and can be transformed to the target tissue. However, the problem of this study was the mechanical properties. The mechanical properties was not good enough. Therefore, we continue this study by changing our polymer from amine terminated group polyethylene glycol to a special natural polymer which is thermosensitive. We use crotin as a polypeptide and modified it by natural polymers, make it hydrophilic. And then we have shown that with increasing the temperature, it's transferred to a gelation and make it hydrophobic. And one of my postdocs, Dr. Eslahi, was successful to show that, as you see in the graph, please note that shows the modulo of elasticity versus the temperature. So at low temperature, the material is fluidable. When it is injected in the body around 37 degrees centigrade in the body temperature, it transforms to a gel. Therefore, it can be used for cartilage tissue engineering. You see the SEM picture of the material and the flash in the right down figure. The flash shows the nanoparticles embedded inside the hydrogen matrix. So we could reach to a mechanical properties which is close to the cartilage, which is useful for people who suffer from the cartilage damage. We were successful to patent it, U.S. patent in 2019, as a frontiers in this research. The other area which I would like to mention is for wound healing. There are a lot of activity for preparing materials and using nanomaterials for wound healing, for skin regeneration and wound healing. Without any doubts, fibrous materials are very important because permeability of the scaffolds are very important. The size of the pores is very important, and the mechanical properties are very important. At the start, we made some nanocomposites by mixing graphene oxide and graphene nano layers with polymeric materials, mostly chitazone, because chitazone is is a natural biopolymer with antimicrobial activity. We have shown that the addition of graphene oxide increases the mechanical properties of fibrous materials and also improve the wetting properties, hydrophilicity, which is important for wound healing applications. And then we did a lot of efforts on cell viability, on live Dave assay, and so on. All examination shows the materials can be used for wound healing applications. However, the main problem was the mechanical properties and elasticity, because the elastic properties is very important, and also the mechanical properties have to be close to the skin. Therefore, in continuation of the work, we did some more effort and use it for with the control of the amount of graphene oxide in the matrix, and doing a lot of in vivo tests on meats. We have found that after adding 2% graphene oxide, the pad which we made can be used in vivo to regenerate skin after deep injury. As you see in the figure, in the left-hand side figure, it's a meat with a wound on the surface, on the skin, and a mat of containing graphene oxide on the surface. And we measure the wound closure, as you see in the right-hand side. We have found that the presence of graphene oxide accelerates the wound healing properties, which is very wonderful. In continuation of this work, we thought that, okay, if we want to add some growth factors, biomolecules, drugs inside our mat, what should we do? The idea was to prepare a core structure. So we use a double nozzle, electrospinning system with double nozzle, and incorporated growth factor and a drug inside and outside of the shell. So one of the materials, the lysosomes, inside as a growth factor, and the outside layer contains a drug. So we would like to have a drug and a growth factor inside our mat in order to accelerate the skin regeneration. As you see here in the TMX structure, we were successful to incorporate and to manufacture the core structure. And in the downside, the graph, I show the release rate of our growth factor and also the drug versus time. As you see, it is possible to control the release rate, and the burst release is very small because it's a multi-layer. I would like to add that without the core shell structure, and incorporation of nanoparticles inside, it is not possible really to control the drug release over a long time period. In following, we try to make it even more active if the skin injured from a very deep injury. So it's not only in the epidermal bar, it's in the underlayer as well. Therefore, we had in mind to prepare a 2B-layer structure. The first layer, as you see in the downside figure, is a fibrous mat, and the upper side contains a hydrogel containing biomolecules and so on. So we made 2 layers. One layer is a fibrous, the top layer is a hydrogel. The SCM picture shows our system, down and top side. Both are proofs, but with 2 different functions. Then we use this material in vivo examination on meats. As you see here, we induce a very deep injury inside the skin of the meats, and add the bilayer on the top and monitor the development of the wound healing process. The result was very amazing. The bilayer structure works much better, at least twice better than a pad and a sponge and commercial available systems which is in the market, because it has a growth factor, it contains drugs inside, it contains other biomolecules that can be used and accelerate the wound structure. The other works in continuation, I was asked by some patients that is it possible to have it like a gel, not a prepaid membrane. We would like to have a gel inject on the body of our patients. So Dr. Medicines asked me whether it is possible to make it. Yes, it is possible. We developed a hydrogel particularly for this purpose to treat wound injuries which are really, really deep. So the Dr. Medicine can inject the hydrogel on the injured surfaces by a nozzle or by a syringe. And the important point is the behavior of the gel is reversible. So during injection is a fluid, after injection is a stiff body. We incorporated chitosane nanoparticles and drug inside our gels. Chitosane is important because it can bring antibacterial effect and also encapsulate the drug inside. In the right-hand side, you see the surface of the mesh after deep injury, after 0 days and after 12 days. You see the injury after 12 days is almost fully repaired. It's an amazing result. It is not published yet. We are going to publish it very soon. But the result shows that this is an effective strategy to attain the regenerate skins. The other topics that nanomaterials are used is for nerve regeneration. As you know, nerve regeneration is a hot topic to now. The problem is for nerve regeneration, we should have a conductive material. Nerve need a conductive material. Most polymers and almost all polymers are not conductive. Therefore, we try to use two-dimensional materials. The best one is mexine, which as mexine have a high conductivity. We use mexine. We develop a procedure to have a special type of mexine based on titanium, carbon, and so on, very conductive material. We added mexine to our hydrogel and use it for treatment of nerve system. The polymer which we use was light active, so using a UV light, we could cure the scaffold. As you see in the right-hand figure, a mesh was cut. The peripheral nerve from the leg was cut for 1 centimeter. We inserted the scaffold and the gel inside by irradiating a UV light. We cured the materials, and you see in the SCM picture, you see the surface after a while. The cells are stick to the surface, and the nerve was regenerated. This is also one of the newest results of our work, which we use mexine inside a curable hydrogel to use it for nerve system. There are other application of nanomaterials for imaging, sensing, drug delivery, and cancer. The first section of my topics was about the regeneration of tissues. I'm going to the second section. I personally like to mention that over the last 20 years, many nanoparticles have already been developed for various purposes, gold nanoparticles, graphene nanoparticles, and so on. But I would like to mention that microbes, we say we need 4 T. First T is trackable. The nanoparticles or any nanomaterials have to be traceable. We should be able to trace the nanoparticles inside the body. It should be trigiable, which means that it should be thermosensitive or pH sensitive to release our biomacromolecules. It should be targetable. So I would like to target it to a special tissues, and it should be tunable. I have to be able to tune the surface properties, the physical properties, and so on. I would like to show you some example from our recent works. The first work, which you know for imaging purpose, many nanoparticles have been used, but mostly they are not in the right wavelengths. We would like to have their wavelengths around 800 to 900 nanometer, so we can image the nanoparticle or the carrier deep in the tissues. Most of them in a green side or in a blue lens, blue light. It's not useful. It only can be used on the surface. So one of the best candidate is lead sulfide. As you know, lead sulfide is a wonderful photoluminescence material. However, lead is very cytotoxic. And we cannot modify the surface by hydrogels, by polymers, or even by metals, because if we put in metals, we lose the photoluminescence. If we use a polymer, anyway, lead will diffuse from the layer and makes it cytotoxic. One idea to create it, to coat it, to cover it with a thin layer of graphene. And graphene is, my idea was whether it is possible to confocaly coated PBS quantum dots with a layer of graphene without losing the PL. At the first, as you see in the downside images, we use computer simulation, DFT simulation, and show that it is possible to passivate the PBS quantum dots by a thin shell of graphene. And then we went to the laboratory and tried to make it. We developed a special procedure, which I'm not going to the details, but I show you here in the TM images that it is possible to have a one layer of graphene on PBS quantum dots conformally coated. And you see in the down pictures that the materials is still shows the photoluminescence intensity even in 1100 nanometer, which is extremely helpful for bioimaging. We did a lot of examination on cytotoxicity, on the biodistribution, and we have shown that in a special concentration, it is possible to use it for bioimaging. However, many of our partners are afraid to use these materials for bioimaging because of the lead. Therefore, we try to make another possibility to make it targetable. It's very important. So we developed a magnetofluorescence, a hybrid particles that can be used not only by magnetic imaging, but also by fluorescent imaging. So this is a dual imaging for cancer therapy. One of my postdocs say, develop a special procedure, an in situ procedure, to prepare magnetic nanoparticle covered by a thin layer of graphene on the surface, the magnetic particle, or decorated by graphene nanoparticles or graphene quantum dots on the surface. So, and then after preparation, she covered the surface by a polycarbonate polymer in order to incorporate drugs and biomolecules inside the polymer shell. So the hybrid system can be transferred to the target tissue by magnetic field. It can be imaged by magnetic and also by fluorescence imaging, and then it can be used simultaneously for hyperthermia. So the particles can be warmed up by magnetic field or by light to release the drug or even kill the cell structure. As you see in the right-hand side images, she was successful to have both magnetic properties and photoluminescence. Afterward, she used it inside the body in vivo imaging. The left-hand side shows in vivo imaging of a cancerous cells in a mice. As you see at various times, you know, we put a magnet there, and then the nanoparticles are collected in the prefrontal area of the tumors, and you can image it. The right-hand cell shows the image after by MRI imaging. And surprisingly, by hypertrema method, she showed that the cancerous cells can be killed over time, which is a relatively amazing result. In following, we tried to modify the shell by better polymers to incorporate biomolecules. And we use amine-terminated PEG system, cover the surface of our hybrid nanomaterials, and then conjugate biomolecules on the top of the ATPEG polymer and use it in vivo to treat cancerous tumors by three effects, not only magnetic effect, but also by light and also by drug. So speed up killing the cancerous cells, and simultaneously we are able to image how the cells and tumors are removed. The next step was to develop more sophisticated hydrogels, which is the dual sensitive. So we wanted to have a hydrogel system, nano carriers that can release drugs or biomolecules via reaction in the body with some enzymes. We developed organic nanoparticles based on polynoric creatinine copolymers, load the biomolecules or drug inside, use self-assembly to create a complex matrix, as you see in the SCM picture in the right-hand side, if it's clear. Hopefully it is clear. The drug is inside. The size of nanoparticles is about 40-50 nanoparticles. When we inject it inside the body, trypsin or glutathione react with the surface, break the sulfonate bonds, and release the biomolecules inside the cancerous cells or any target tissue. We show that the system works very nice inside the body of a meat. As you see here, we monitor the trace of biomolecules. In the right-hand side figure, you see the blue line shows when we don't have any enzyme in the system. So the nanoparticles are stable inside the body. The top curves, yellow and green, shows when we have trypsin or glutathione, which is the enzyme or biomolecules which are normally present in our human bodies. So it seems that in the presence of enzymes, the drugs can be released that can be controlled in a specific tissue lines. Again, we asked by our partners, can you make it even more attractive so we can use ultrasonic to release the drug? So one of my PhD students tried to develop a dual sensitive hybrid nanoparticles, especially for breast cancer. Our idea was to have an injectable nanoparticles that can be injected inside the cancerous tumors inside the breast, and using a lamp, exon lamps, we can image the tumor, and simultaneously by ultrasound probe, we can release the drug and kill the cancerous cells. We use silibene or silibene as a model drug and prepared the nanoparticles. The nanoparticles was based on liposomes. So we use a liposome system, a special liposome system. Inside the liposome, we put the drug, and the outside layer, a thin layer of graphene quantum dots. So it can be imaged, and the polymer which we used was a piezoelectric polymer based on PVDF. So it's a very complex system, liposome, PVDF, quantum dots of graphene in order to create multifunctionality. As you see in the graph side, the release rate of of the anti-cancer drug versus the time of the ultrasound. So she could successfully show that by ultrasonic wave, we can control the release rate. And also, we try to examine the two flow cytometry to show that whether necros or apoptosis exist. And interestingly, when we use our anti-cancer drop only with our polymer, we could see some kind of necros, which is not good. But when we made the hybrid nanoparticles, mostly apoptosis occur for cancerous cells, which is more desirable for our practical applications. I would like to end my talk with some example of biosensing by nanomaterials. For example, I would like, as you know, diabetic illness is one of the major problems in our country and in many other countries. It's very important to very quickly measure glucose in the body, in the blood, and so on. We develop a special sensor based on gold nanorods for enzymatic detection of glucose. Of course, it can be for other biomolecules, but we try to use it for glucose applications. One of my PhD students developed a special procedure to grow gold nanorods in an order structure on a template, and then try to load glucose enzyme on the surface and to make an electrochemical sensor to detect very quickly glucose inside the blood of diabetic people. Okay, the result was nice, but not very outstanding compared to the other existing materials. Then we decided to incorporate graphene oxide nanosheets in between the gold nanorods. We have found that the enzyme will functionally conjugate to the surface of functional groups of graphene and graphene oxide, and then the gold nanorod transfer the electrons and makes the detection very, very quick and very precise. She showed that the system works extremely good with high performance and quick, and we examined it even in the laboratory, and we tested with the laboratory detection, which we done usually every day. However, there are a lot of interest for non-enzymatic biosensing. For this purpose, we also developed another biosensor based on zinc oxide nanorods, and then we conformally coated the nanorods by graphene oxide nanosheets. And we use nickel as a redox system to oxidize and reduce glucose and glucose oxide in order to detect. And she showed that even the detection limit better with a vast range of linear range. So it was one step forward to preparing biosensors for biomedical applications. The other systems that, the last one actually I would like to mention as a case study was to prepare porous graphene nanoparticles for biosensing. We developed a special procedure to prepare three-dimensional, highly porous conductive graphene materials as a substrate to make freestanding biosensor for many, for detection of different biomolecules, especially for pharmaceutical applications, melatonin, vitamin C, and so on, drugs, and so on. The problem, what we use CVD, chemical vapor deposition, and we created three-dimensional, highly porous, one-dimensional graphene on the surface of nickel foam, and then remove the nickel foam and prepare freestanding three-dimensional graphene, and then surface functionalize the surface. As you see here, the SCM picture on the right top side shows the structure of three-dimensional graphene. As you see, the structure keeps very large pores, creates a lot of surface for biosensing. On the other hand, the ballistic transport of electrons in graphene creates tremendous opportunity for biosensing applications. And then we decorate the surface by electroactive materials that can be any nanomaterials, gold or anything, and use it and made it, as you see here in the downside chip, a freestanding chip based on, we made an electrode that can be used for electrochemical detection of various biomolecules. Just to show some example of what we did. For example, we use yttrium hexacyanoferrite flower nanoparticles on the set. You see it's like a flower on the surface of three-dimensional graphene. And we use it for melatonin. And we show that melatonin, which is a factor for sleeping, can be measured very quickly and very efficiently in drugs or in pharmaceutical applications. The second example, we use boron nitride nanoparticles. We develop a special procedure to prepare boron nitride nanoparticles and then cover the nanoparticle on the surface of three-dimensional graphene and use the system for detection of ascorbic acid or vitamin C in various products. The next stage is we use gold nanoparticles with various shapes, and we show that this system can be effectively be used for biosensing of many substances and biomolecules inside the blood or in water or for water purification and so on. I would like to conclude my talk by one word, and this sentence is: really there are plenty of room for development of nanomaterials for biomedical applications. Undoubtedly, there are a lot of frontiers. I only try to show some examples. Of course, there are other examples for different applications. What I reviewed, it was what has been done in my research group in recent year for tissue engineering, for sensing, for imaging, and so on. And I'm quite sure the other lecturers could add to this. I would like to thank you for your attention to the organizer IOC. I am very sorry, I don't know what is going on. I know that the Zoom is filtered in Iran, so might be this is the reason that I could not load my presentation effectively. I am sorry for that, but it was out of my range. Thank you very much, and we'd be happy to answer any question that might be exist. Thank you very much.
Thank you so much, sir. And absolutely, that was fine. These are some of the tactical glitches which often happen when we conduct virtual events. So thank you so much for wonderful, informative lecture. And if any of the audience have any question, you can type in the chat box, or you can raise your hands. So I can see appreciation of your lecture, sir, in the chat box.
Yeah, I see the chat box. If how do we determine the linear range of sensor? Okay, this is a very principal question. We usually make a calibration curve. Depends. We measure it, we compare it, make a calibration curve, and then by a SN ratio, which is very normal electrochemical book, you can just look at it. Usually we take SN equal to 3, and then by extrapolating the calibration line, we measure the detection limit and linear range of sensor. Of course, there are some controversy inside, because sometimes there is not really a linear range. There are two linear range and even more. In my experience, usually we use only the first part of linear range of detection limit. The second question, nice presentation, thank you. Okay, is there any question? Please type it. I will try to answer it.
Thank you so much, sir. I think it
Thank
was
you very much again for inviting me. And I hope that next time the condition will be better so I can be more effective in presenting and giving talk.
looking forward. Thank you so much, sir. You have a good day. Thank you everyone for participation.